Okay, so far what we discussed is a pulse modulation, right? So we have our input is originally analog, okay, and analog signal will be converted to digital by ADC converter. When you use that in the circuit, as we discussed, we can use the pulse modulation. But what we are seeing here in this diagram is a general baseband binary data transmission. So we have a source input. This is a binary data. It's going to be either 1 or 0. Okay? And that's the original information that we want to transmit. Right? And here you see that from here to here is our transmitter. In the middle here we have a channel. This channel in general is wireless channel or wire channel or underwater, anything. This is just a channel, any channel. And here is a receiver. Okay, here's the receiver. In general, in every circuit, every transmitter, we have a transmit filter. Right? So this is the information we transmit, binary information. But at the end of the transmitter, we have a filter. We call that transmit filter. At the receiver, also, we have an antenna right here. But after the antenna, we generally have a receive filter. And then we have some demodulation right here. Okay? So we have a modulation here. Of course, we have a demodulation at the receiver. But after the modulation, we have a filter. Okay? And then you transmit over the antenna. And the receiver, you receive the signal over the antenna, and then you apply the receive filter. After that, you do demodulation. So what we're going to discuss here is why do you have a transmit filter? Why do you have a receive filter? Why do we have transmit filter? Okay. One reason, many reasons actually. One reason is that you need to make your spectrum. So what you're doing is you are transmitting a signal over here, right? You have antenna, transmit antenna here. And before transmit, you need to shape your transmit spectrum signal, your signal spectrum. Okay? So you need to massage spectrum. Okay? Think about this way. This is, let's say, wireless channel. Okay? Wireless channel, you cannot use any frequency. You are supposed to use your own bandwidth. Let's say you think about your cell phone. Cell phone is using 1.8 gigahertz. And your bandwidth, let's say, is a 10 megahertz. Right? That's the only frequency bandwidth you need to use. You are not allowed to use other bandwidth. Right? Other frequency, you should not use it. So the government or the organization asks you to satisfy some filter, some spectrum mask, what we call a spectrum mask. What that means, let's say this is your frequency, F1. So from here to here is your bandwidth. And in this region, it's used for someone else, right? It's not for you, right? Someone else is using this frequency. So when you transmit a signal, your signal should be only inside here, because this is your bandwidth. The specification will tell you that you need to satisfy this kind of mask, spectrum mask. So what that means is your spectrum will be only here, and when you make your spectrum should be under this mask, like this. If your spectrum goes over this mask, then you're out of spec. Okay? So that's why we need a filter. So you're gonna make your spectrum to be spec compliant, and you need to you should not transmit this out of band spectrum. This is what we call as out of band, because this is not your band, this is someone else's band. It's out of band spectrum. So you need to reduce the out of band spectrum because you are interfering other users, right? So that's why you need a transmit filter. And we have a channel. And why do you have a receive filter at the receiver? Basically same reason, similar reason. When you have an antenna at the receiver, basically you're receiving all of the different frequencies. But you don't care about other frequencies. You are only interested in your own frequency, right? Which is this area. So that's why you want to have a filter which filters out all the other frequencies, and you are going to receive only your bandwidth. That's why you have this one in general. So what we are trying to see here is, in the system, here to here is a transmitter. This here is a receiver, right? But when we put everything in the block diagram like this, what we are trying to do is we want to group these three blocks together. This is a part of transmitter, this is channel, this is part of the receiver, but that's okay. We just group them all together. Okay? In this model, we are group these three, and then make this as a one block, like this, as a PT. Okay? In frequency, it's a PF. So this transient filter, in frequency domain, we have a frequency response GF. Channel, we call it as HF. Receive filter, we call it as a QF, okay, in frequency. So we have three different blocks, but put them all together, make a PF. Okay, once you change this model into this way, what is the goal of this PF? Think about this whole thing is just one block, like this. Then what is the ideal block of this one? What is the ideal response? Eventually, the input to this block is binary data, 0, 1, 0, 1 kind of thing. And what is the output here? It's again binary, some signal. So what do you want to do? How do you want to make this block in order to make an ideal communication? Simply speaking, the ideal block of this, we need to avoid the intersymbol interference. Intersymbol interference. Okay, what is the intersymbol interference? This is a very, very important concept. Okay. Let's make a simple, very simple example. What I'm doing here is just general block diagram. We have a block, okay, PN. PN is impulse response of this block. Okay, we have a block and we have an impulse response of this block. Xn is the input, and Yn is the output. You know impulse response, right? So what is going to be? What is the ideal impulse response of PN? The ideal impulse response is simply like this. That's going to be perfect ideal impulse response. Because when you have this kind of the impulse response for this block, what that basically means is your output is exactly same as input. Okay? Why? Because what this impulse response tells you is that this block does not add any delay, no delay, because in time domain we have a 0. No delay, and the output you are multiplying 1, right? So inside this block there's no delay, and the output is multiplying by 1. So in that case, Xn just bypass, right? What if we have 2? Again, in this block there's no delay, okay, right? No delay, and Xn is now becomes double size, and then go to the output. So again, it's almost ideal, because this amplification always can be reduced. So amplification doesn't matter. So again, this is very ideal. So this amplitude value, we don't care, right? Now what is important is, let's say this is not 0. We have 1. What does that mean? 1 means now we have a delay. In here, we have a delay, right? So what's going to be the output in that case? Let's make it 1 anyway. So make it simple, 1. So if we have this kind of block diagram, the impulse response for PM, what is going to be the output? Simply speaking, think of a simple way. This is an impulse response of this one. No amplification. The amplitude still same because it's 1, but we only have a delay, and delay is 1. And this is what I'm drawing is a digital signal, right? I say n, right? T probably is a continuous time, but this is n, so digital signal. So what is going to be the output? Simply the input, and you are adding 1 delay, like this, right? Something like this, right? Simply. It doesn't matter what is your input signal in this case. Maybe your input signal is very complex, or there are many different information. Doesn't matter. Because inside this block, we are adding only 1 delay, like a flip-flop or something like that, right? So that's what happened in this case. Okay? Now then, let's make it a little bit different way. Now we have 2 taps. 1, 0. The other one, 1. So let's say this is our impulse response of this one. Now what happened? What happened is, it's basically superposition, right? You're adding 2 outputs, yn. What is the output if we have only this one? Then it's xn, right? If we have only this one, then this one has no delay. Therefore, the output probably was xn. However, we have one more tap. Okay, the output from this tap is going to be xn minus 1. So we're going to get this output, right? If we have this impulse response, we have this one, right? Okay, now let's think about this case. Yn equals to xn plus xn minus 1. Okay, let's think about this way. Let's bring up some xn. Xn, let's say, is just an example here. Let's say this is our xn. Okay, this is our xn. Now then, what does yn looks like in this case? As you see here, yn is xn plus xn minus 1. So let's do that here. Xn is like this. This is xn. And let's think about xn minus 1. Actually, it depends on which one you see first. Let's make it as a 0, 1, 2, 3. Okay, so this is a time 0 or sample 0, sample 1, sample 2, sample 3. So this is a first sample, next sample, next sample, next sample. Okay, in that case, the when this sample goes in, this one goes in first. Okay, maybe it's a little bit confused, but this is sample 1 or sample 0, sample 1. So sample 0 comes in first, and sample 1 next, sample 2 next. Okay, you understand? In that case, you need to flip it and then put it, right? Because this one is an earlier sample. Okay, think about that way. So same way here, we can say this is a first or 0 sample, sample 0, sample 1, sample 2, sample 3, something like this, right? Same way here, sample 0, sample 1, sample 2, sample 3. Think about some same way. Okay, in that case, So simply speaking, the xn minus 1 is a shifted version. Okay, shifted version by 1. So you just do one shift. And then what happened? This is xn minus 1. Now you're going to add these two. Then we're going to get the output, right? Here, 0, we get this sample. This one plus this, it's bigger, like this. This one plus this, a little bit negative. This one, a little bit positive. Here, this one. Eventually, this is going to be like yn. Something like this, right? Simply, you are adding these two. That's your output right here. Yeah? Now, the problem is, we are talking about communication systems. You are transmitting some signal, and you want to recover that signal. Now, the problem is that you transmitted this signal, but you received this signal. Okay? This is what you receive. So from this received signal, how do you recover this? That's a problem. I'm receiving this one. This one definitely looks very different from this, right? So how do you recover from this one to this? That's the question. And why? And before that, why do we have this kind of signal? What was the problem? We want to get the same one, right? But instead, we are receiving this. Why is that? Because some samples are added like this way. Or another way, we are basically adding xn plus xn minus 1. If we have, let's say, one more, 2. Okay, if that's the case, then we are adding one more, like this, right? Things are more and more complex, and the signal is now even more difficult, even more different, right? So now the problem is, then let's look at this one. How do you see this kind of impulse, this kind of response? We are getting output. Output is not just same as input, but this is a, what do you call this? xn is the input, xn minus 1 is. We typically call that as this is something like this, right? Let's say I'm go up into mountain, and I just say then I hear my voice, right? That's echo. But the problem is when I say then I hear my voice. Now not just once, right? Like that, right? That's echo. So that's exactly like this. I say my voice, but when I hear my voice, I hear something like this, right? With a little bit delay. With a little bit later, I hear it again. A little bit later, I hear my voice again. That's exactly what happened here, right? This is what we call as a ISI, intersymbol interference. And from the system point of view, from hardware point of view, what this basically means is when you have xn minus 1, that means we have a memory inside. So think about this way. Again, go up to the mountain, right? I want to hear my echo, my voice as echo. So why do you hear my voice again and again? Because inside the up in the mountain, there is a memory. Okay, that's how I see it. That's how we see the system. There is a memory. So when I say that goes into the memory. Okay, and then memory. What is memory? Memory basically keeps the some value, right? And outputs a little bit later after a little bit delay. So the mountain basically has a memory, and when I say that goes into the memory, right? And gives me back a little bit after delay, right? A little bit after some delay. So same thing here. xn, in this case, there's no memory because we have n input and you get the output exactly at the same time. So in this case, there's no memory. But this one, we can see that there is a one memory. Because when you put some signal like this, but you are going to get the same signal with a one time delay, right? You are not going to get exactly the same time. The sample 0, you are going to get a sample 1, right? Sample 1, you get a sample 2. So there is a one delay. How do you get the one delay? Because there is a one memory here. Same thing. If you have, if you see this kind of signal, that means you have memory, but that memory has a two times delay. That's how I see it. That's how we see this system. Do you understand what I'm saying? Yeah. From the system point of view, that's how we see it. So this is like a memory. But in general, what happened is, in this case, see here, let's look at here. This is the first sample. This is second sample. But this second sample is now added with the first sample. This one and plus this, right? Same way, this sample 2 is added with the sample 1. But actually, sample 0 is the previous one. So what that basically means is sample 0 and sample 1 is added, and sample 1 is interfering the sample 2. Sample 2 is interfering the sample 3. That's exactly what happened. So that's why we call this intersymbol interference. Each one is a symbol. Okay, each one is symbol, but each symbol is interfering the next symbol or even next symbol. Why? Why do we have this intersymbol interference? Yes, memory, but in this case, why do we have this intersymbol interference? Because our impulse response have this one. Okay? In this block, we have a delay. We have a multiple taps, like 3 taps, and each tab has a different delay. Okay, so because of that, when you have a two taps, we have a 2 outputs like this. But this one has a different delay, right? So therefore, we are going to get this kind of intersymbol interference. So this is a very bad one. Intersymbol interference is bad. And ideally speaking, we don't want to have an intersymbol interference. What we want is we have xn as an input. We're going to get the yn as an output, and hopefully yn is same as xn. In order to get the output yn to be same as xn, we should not have intersymbol interference. Or in other words, we want to have this impulse response. This. Just one tap, right? That's what we want. So ideally speaking, that's what we want to do. We just group all them together, make a PT or a PF, okay? And impulse response of this particular PT should be this one. Just a one tap impulse response. That's the ideal scenario. Okay, that's what that means as a whole thing. So this whole equation is a mathematical way of showing all that. So let me tell you a little bit on how to do that. In here, right, we group these 3 blocks together and make a PT. And let's think about this one as AN. AN is going to be input to the transmit filter, and YT is the output of the receive filter. You know the ST. Here is ST, right? ST equals to convolution of these two, right? Input and this one. Convolution of these two. Now the XT is a convolution of these two, right? But this ST is a convolution of these two. So therefore, this XT is a convolution of the whole thing. Same way, here, YT. YT is a convolution of the whole thing. Do you understand what I'm saying? Let's see. let's call that as xt. Okay, so that is what we see in that block. So what we are doing is we want to group these three blocks together and make a PT. But PT is actually a convolution of these three blocks, GT, HT, QT. We have three different blocks, but these three different blocks are one after another. So when you put them together and make a PT, this PT is the same as a convolution of these three blocks. Right? Because this ST right here, this ST is a convolution of this AN input signal with GT. But this XT is again same way, convolution of ST input and HT. But ST is this one. So put this one here. Then XT is the same as convolution of this one, this one, this one. Same way, you can do the YT, right? What is YT? YT is going to be the convolution of QT, XT. But XT is convolution of these three. So therefore, YT equals to convolution of QT, HT, GT, AN. Convolution of all these four. Right? Or in other words, we can just put them all together, make a PT, right? Like this. Like this. What we are doing here is we just make it this way. Group all them together and make one block like PT. Okay? But PT actually is this one. So our output YT is GT is a PT convolution with 8AN, but PT actually is a convolution of GT, HT, QT, because the PT is a group of these three blocks, like this, right? Simple like this. That's how we change this whole thing into this one. Okay, that's what these slides will tell you. But what we are trying to see is that what is the best way to design this block? That's what we are trying to learn in this chapter. Okay, how can you design this block? That's the important message. Let's look at inside here. We have three blocks. Let's look at this first. Channel. We cannot control channel. Okay, this channel right here. Maybe this channel is wireless channel, or maybe underwater, or any channel, any kind of channel. This channel typically is given to us. We cannot make, or we cannot change. We cannot control. Okay, so this is completely given to us. Whatever channel we have, we cannot control it. However, transmit filter, receive filter, that's under our design, because this is a part of our transmitter. This is part of the receiver. So we can make our own transmit filter, receive filter. Okay? So how to do that is we measure the channel first. Okay? We measure the channel and find out HF or HT. Okay? So HT and HF is given to us. Now based on that, we're going to design this transmit filter and receive filter in order to make ideal block or PT. And what is ideal PT? Ideal PT should have this impulse response. So our goal here is to make this whole group, like a PT, to have this impulse response. We want to make this PT has this impulse response. That's our goal. Okay? That's our goal. So mathematically, what we are seeing here is that one. What is this one? This is a convolution, right? AM, this is the input. That's what I'm showing here, the input. And YT is the output. But how do you get the YT output? That is convolution of AN and PT, right? So that's what it is. AN and PT, this is convolution, simply. Right? That's just convolution. So that's convolution. And when you have this kind of convolution, we have a sigma. Sigma is K from minus infinite to infinite, right? This is an infinite summation. But now when you look at this infinite summation carefully, then we see that there is a 0 here. When K equal to 0, then we see that this is A0 Pi, right? And just to make it out, just to make it separate. So that's what we see here. Okay, that's what we see here. No, actually, in this case, we just bring out when the index is I. No, actually 0, right? 0. Yeah, when K to 0, then just make it 0 out. Why do we make it 0 out? Because this is we want to get this kind of impulse response. So when K equal to 0, when time equal to 0, we just make it separate like this. And all the other summation term, we just leave it here. Okay? And these other term will contribute to make an intersymbol interference. And this one, this term, that is what we want here. That is what we want. Okay? Yeah. So that's this is same as this one, right? We have AN input signals, and when you do convolution, you're going to get the output, right? And what we are trying to do is we want to make a output to be exactly same as input, right? That's what we want. We want to make a output to be same as input. In order to make output to be same as input, we need to have this impulse response, right? But generally, this one does not have this one, this impulse response. Generally, it has some other impulse response, like some other things, right? So in order to avoid the intersymbol interference, what we need to make sure is we need to make this term will be 0. If you make this term will be 0, okay? If this one intersymbol interference is 0, what that means is, let's look at here. Yi equals to some constant times AI. What is AI? That's input. Our input is AK, right? So this is input, our input. And your output equals to just some constant multiplied by input. So that's what we want, right? As I said earlier, we want to get the output to be same as input. And that's the condition that we want to make. But in order to make it, all the other term, we need to make it 0. Okay? That's the intersymbol interference. Okay, let's continue next.